Welcome everyone to week 2. Before we get started on new material, let's quickly recap the key messages from last week. As I mentioned at the start of the course, when we began by covering the math behind neural network optimization, it's okay if you can't get your head around matrix calculus. As we go forward, PyTorch will abstract all that away for you. The key points you need to remember, however, is how the design of the architecture impacts network parameterization. In other words, you need to know what size or shape you want your weights matrices. At the same time, when designing and debugging networks, it helps to understand the constraints and limitations of different components to understand what can go wrong. Last week, we focused on fully connected networks composed of linear layers. For these, the input features are the number of neurons in the previous layer, and the number of output features are the number of neurons in the given layer. This is because each neuron in layer L is connected to every neuron in layer L-1, and the weights matrices are therefore learning to combine the activations of the previous layer, which is 1 per neuron, with new linear combinations for each neuron in the current layer. Finally, we learnt when building classifier networks, it's common practice to use a sigmoid or softmax for the output neuron, since these are constrained to sum to 1 and therefore return class probabilities. Otherwise, variants of ReLU activations are more common for hidden neurons. So having said all that, can you tell me what the dimensions of the following weights matrices should be for this 4-layer network? Answer this in the recap quiz on Keats. Next, we look at PyTorch, which we strongly recommend over TensorFlow, at least while you're learning, since the syntax is cleaner and easier to follow, and you can debug with standard IDEs. Last week, we went through the basic and consistent structure of PyTorch network classes and the key components of training loops. For network classes, you inherit from the nn.module and overload the constructor and forward function. In the constructor, you define your layers and their parameterization. In the forward function, you piece together the layers in order. One thing we didn't mention, but we will cover this week in the notebook, is nn.sequential blocks. These further tidy up class definitions and improve training efficiency by preventing the network from keeping track or saving all intermediate stages of computation. Finally, in terms of training loops, we saw how for standard CNNs and fully connected networks, we must remember to clear the gradients. We then make a forward pass by passing inputs to the network. The nn.module handles the rest behind the scenes, and after that we calculate the loss for the resulting prediction, backwards propagate on the loss tensor, and update the network parameters. Two things that we didn't cover, but you might have observed from the training loops we gave you last week, are that you always need to set your network to training or evaluation mode before training, testing, or validation. Here, evaluation refers to testing and validation equally. The second thing you need to do when training on GPU is move your data batches to the device at the beginning of each loop. So looking again at the example for the MNIST MLP classifier from last week, this is where we set the training mode for the training loop, and eval or test mode for the validation loop, and here is where we push the tensor to the GPU device. In the first part of this week, we will go on to extend these concepts to implement a CNN for MNIST. Remember that as you move from MLPs to CNNs, your training loop structure isn't impacted. What you need to be changing is your network design. So that's it for this quick recap. Please now go on to the materials from session 1 for this week.